All right, so super excited about today because we are going to be starting to talk about the chain rule. So what the chain rule does is it allows us to differentiate functions that are plugged into each other. So for example, when you see something like y equals, you have the square root of x cubed plus 2. Really, you have two different functions here, right? Like you have the square root of stuff, and then you have your stuff, which in this case is x cubed plus 2. In this function, y equals sine of x squared, you have sine of stuff, and then you have the stuff, which equals x squared. So whenever you see like a function inside of a function, we know that we need to take the chain rule. So let's talk about like how do I take the derivative of a function plugged into another function? It is pretty straightforward, so it looks way more complicated than it actually is, but the chain rule states that if you have a function plugged inside of a function, so in this case g of x is my stuff, then if it's differentiable, you would have f prime of g of x times g prime of x, or f prime of stuff times the derivative of said stuff. So let's kind of start doing a little bit of practice here. And I want for us first, just to prove that it's the exact same thing, if we're given the function f of x equals 5x plus 3 squared, I can think about this as stuff squared. So we have two functions here, right? We have f of x is stuff squared, and then the stuff is 5x plus 3. So let's look at this without the chain rule and think about what we would do, and then let's look at this with the chain rule. So without the chain rule, you guys know that you would fully expand, and you would say, all right, I know f of x is 25x squared plus 30x plus 9, and then f prime of x is going to be 50x plus 30. So now let's look at it with the chain rule. So that one was pretty straightforward. With the chain rule, I'm going to say f prime of x is going to be, remember you differentiate the outside, so 2 times 5x plus 3, take it down a power, so that's a 1. And then we're multiplying by the derivative of the stuff, or the inside. So the derivative of 5x plus 3 is 5. What that looks like here is 10 times 5x plus 3. And if I look at that, and that 10 were distributed, it would be the exact same. Now you may have thought, well, I don't want to learn something new because feels like it was easier to use it without the chain rule. But once we start raising that degree even more, the chain rule is going to be even more impactful. So let's raise our inside function to the third power. Now, could we write this out 3 times and multiply it out? Yes, of course, but you guys, we all know, ain't nobody got time for that. So let's get this done here. I'm going to say f prime of x equals, so the derivative of the outside function, let's get some color coding going on here. So that outside function is something squared, or cubed, my apologies, and then we're multiplying by the derivative of the inside function. So we don't touch the inside, and then we derivate the inside. So what this is going to look like is we're going to have 3 times, right, 4 minus x squared, squared, and then we need to derivate the inside function. So then we're going to multiply. The derivative of 4 is 0. The derivative of negative x squared is going to be negative 2x. So when we rewrite this, we can leave it like that, honestly. Or I can say, all right, I know that that 3 and that negative 2x can be multiplied, and I can get negative 6x times 4 minus x squared squared, and leave it. So remember, both are okay. Same, same. So let's work out a few examples and get it a little bit more complicated because we always want to be, right, like pressing forward, let's move forward. So here I'm going to rewrite f of x as x squared minus 1, And this is going to be to the 3/2, right? Because that root index is a 2. And remember, we write it the exponent over the root index. So we have two different things going on here. If we go back and look at my rule, your outside function is that those parentheses raised to the 3/2, and your inside function is going to be that x squared minus 1. So let's start getting this written down here. I'm going to say f prime of x equals, remember we don't touch the yellow, we just derivate that green first. So I'm going to say 3/2 times x squared minus 1. Remember, we're subtracting that exponent by 1, so we're subtracting 2 over 2 because that's the equivalent form. So I get that to the 1/2. Now I need to multiply by the derivative of that stuff, or the derivative of the inside. So that's going to be times 2x. We can leave it like that, or we can simplify, and we can say f prime of x equals, let's say, I'm going to combine these, so 3 times 2x is 6x. I'm going to just rewrite this as x square root of x squared minus 1, and that's all going to be over 2. And then if we wanted to take it even further, we could simplify right there and leave that 3x square root of x squared minus 1. So always an option here, but remember any of these forms are equivalent. All of them work. So unless it says put it in simplest form, then you don't have to worry about it. Let's check out this next guy right here. We are going to have -7. I'm going to rewrite this as -7 times 2x minus 3 to the -2. Just pulling that up. So then when I say f prime of x, remember we have our outside function, which our outside function is this business going on here. And then we have stuff in the inside, which is that 2x minus 3. So rewriting that, I would get 14 times 2x minus 3 to the -3. Remember, we don't touch that inside. And then we're going to multiply that by the derivative of the inside, which in this case is 2. So again, if I were to simplify this, you would get 28 over 2x minus 3 cubed. And you can leave it like that. I want for you to take a moment and pause here and work on C and D. I'll highlight. There's the outside, so that E is the outside function, and then that stuff is going to be like, what are we plugging into, or what are we plugging into that outside function? So we're plugging that 3x squared into the exponent of E, and then we're plugging that 5 minus 4x squared into Y. So take a second here, and then check your work and see how you're doing. All right, guys, quick check here. For that very first one, any of these forms are equivalent. You should have pulled down that 2/3, reduced it by 3 over 3, so that's going to be to the -1/3. Remember, we don't touch that yellow or that stuff. And then we take the derivative of that inside, so that would be -8x. Multiply that all out, and you should get one of those equivalent forms. Same thing going on with letter D. Remember, the derivative of E is just E, so it stays the same. And then we touch that yellow, or the derivative of that stuff, which in this case is 6x. Let's have one more chance here. And let's look at what's going on with E. So take a moment and do E, and then we'll come together and do F together. All right, guys, checking in with E. We're multiplying that -2 by that 1/3, getting that positive 2/3 coefficient. Then we have that -4/3 because we subtract 3 over 3 from that -1/3. And then we're multiplying by that derivative of the inside, or that 6. So check right here. Now, this last one is going to be a little bit of a doozy. We'll look at some tables really quick after this. But this guy's a little bit of a doozy because we have a lot going on here. I'm going to rewrite this as cosine of e to the 5 theta cubed, just so we kind of get a feeling about like what's going on here. So we actually have 3 different functions happening. We have a far outside function, so that's that 3. Then we have one set of stuff, or that cosine, and then we have a second set of stuff, which is that e to that 5 theta. So we're just going to work this out methodically, same way that we normally would. And I'm going to say y prime is, we're going to have 3 cosine squared e to the 5 theta And so what I did here is I took that 3, made it a coefficient, and then reduced by 1. So that went from cosine cubed to cosine squared. Now we're going to take the derivative of this cosine, e to the 5 theta. So the derivative of cosine is negative sine. So that's going to be times negative sine. We still have that e to the 5 theta. And then we're going to manipulate that e to the 5 theta. So once I do that, the derivative of this guy right here is e to the 5 theta. But then I have one more that I have to manipulate, and it's that 5 theta. So then we have times 5. So I actually didn't grab that at the very beginning. We should have said, we have so much going on here. So first off, we did the green function, took the derivative of the green. Don't touch anything. Take the derivative of the yellow. So that's that sine, don't touch anything. Take the derivative of the blue. That's that e to the 5 theta. Don't touch anything else. Then we're taking the derivative of that 5 theta, and that gives us 5. Especially when it gets out this long, you could just leave it as is. If you were to simplify it, it would be a little bit of a mess, so I would probably just put a box around it and call it a day. Know that on the AP test, some answer would probably have, right, so you have negative 1 times 3 times 5, which is 15. Then you would have e to the 5 theta, and then we'd be multiplying by cosine squared of e to the 5 theta times sine e to the 5 theta. And all I did was simplify because I took that negative 1 in front of the sign, and I just combined all of that. So this would be more of your AP answer. However, this is totally okay for FRQ, or short answer. It's an equivalent form. We are going to look at one more piece here. And we're going to say, like, how would I use chain rule looking at tables? So really rarely, guys, will you use chain rule like 1,000,000 times like we did in that function. Normally, you'll use it like once or twice. Just wanted to kind of play around with that one. We'll have more practice on that tomorrow. But let's let g of x equal f of 4x. So the first thing I'm going to do is, like, let's say, what is the equation for g prime of x? My outside function is that f of x. So I'm going to say f prime of 4x. Then we're multiplying by that derivative of the inside. So we're multiplying by 4. Once I get to this point, I'm going to say, all right, let's get some values from this table because I'm trying to look at g prime of 0.2. So what I can do is I can come in here and I'm going to say, all right, let's evaluate for f prime and then multiply by 4. So just like before, I'm going to be plugging in that 0.2 for every x. So I have f prime of 4 times 0.2 times 4. So what this is really saying is f prime of 0.8 times 4. F prime of 0.8 is given to us. That's 1.125. And when I multiply that by 4, we should get g prime of 0.2 equals, and I'll have to pull up my calculator. Oh, no, actually, we don't need that. And when we do that, we should get 4.5. So I'm going to take it to one tiny little extension really fast. Let's say that it asks us, so this is true, this is all we really had to do here. But let's say, just to play devil's advocate really quick, let's say it asks us about a tangent line. Well, I know that g of x, or g of, we're evaluating at 0.2, would be f of 4 times 0.2. Oh, and we don't even have the table for that, do we? It's because that would just be f of 0.8. Okay, well, if we knew what that value was, we know that that's going to be y minus that output, right, f of 0.8, equals that slope, or 4.5, times, just realized that I was running out of room, x minus that x value, which is 0.2. So if we had more table values and I knew what that function was, I could plug that in. So guys, just thinking about practicing your chain roll, and I will see you guys in class.